Hello, welcome back. We're almost coming towards the end of the topic in algebra. Before we start, we have done a bit of algebra, then we went into a bit of coordinate geometry, then we came back to algebra, and we seem to be continuing with algebra. But you require all this background information because when you do differentiation and integration, some stage you'll come across any one of these things. So you need to know them. So we are still in the topic algebra. And today I want to talk to you about logarithms. The nightmare of students. Because you people are lucky, 2014, so you got your calculator, so you don't have to bother. But when I sat my A-level exam, I had to work in the exam 3.142, especially the physics paper, times 2.82 power 5 divided by 12 minus 1.92, and the whole thing multiplied by 9.8, 1.92 squared, something like this. 12 times 1.92 squared or something. And I had to give the answer to 3 decimal places, and I didn't have a calculator. Then I used logarithms. Because students are so good. You see, that's how logarithms developed actually. When people came across mathematical calculations like this, they found that it was near impossible or it's going to take ages. So they developed a function called the logarithmic function, which simplified multiplication became addition, and division became subtraction. So they could superimpose, convert all the multiplication to addition and all the division to subtraction, and once you get the answer, convert them back to the number you require. That means we have to find a relation between a multiplication and addition, or division and subtraction, something like that. So that's how the concept started. It was the first man to formalize it started with one Professor Briggs way back in the 17th century, and then it was Napier who developed the concept of logarithms the way we know it today. And of course, that's why some of your teachers might have told you the letter E, which is attributed to Euler. When you do log with a base E, you're looking at a Naperian logarithm. That's again a way of honoring Napier, who developed logarithms in the 17th century, 1600 something. So to understand this, suppose I wanted to do, just to give an example how life becomes easy. Suppose I want to multiply 2 power 15 times 3 power 12. Imagine you have to work 2 power 15 and 3 power 12. When I was in pre-university, I'll call this as y. I would say log y equal to 15 log 2 plus 12 log 3. That is 15 times 0.3010 plus 12 times 0.4667. This, of course, I would be able to multiply and then work out. Let me see, 15 0 0, 15 1, 15 0 1, 45. 4.5150 plus 12 sevens are 84 8 plus 72 plus 8 88, 72 plus 8 88, 12 4 are 48 plus 8 56. So that's something like 4 5 1 9 9 point. Then I would do 10 power 9 10 power 0.9154. That means I know the answer is of the order of 10 power 9. 10 power 9 or more. 10 power 9 means 1,000 million, which I think is a billion. Yeah, the order is in terms of a billion. You see, I didn't have to do 2 power 15. I didn't have to do 3 power 12. I use logarithms. Can you imagine? The last time I used this was somewhere in 1966. when perhaps your dad was born. I used it that time, and because I've used it so much in my school career, these numbers, they have stuck somehow. Log 3, log 2, root 3, root 2. If you talk to any, look, even today, children in India, children in Bulgaria, children in China following the local syllabus, or children in Kenya, they don't have the luxury of calculators. They use a table, they use this method. Only when they go to university, they are allowed to use a calculator, and sometimes you are not even there. I don't think I have, at least in our time, the calculators weren't invented. But these days, the calculators are invented. Still, the educational authorities in India feel that the students need to learn to work without a calculator. So, like, if this came in the exam and your calculator battery was gone, you would be stuck and you would leave it, or you would struggle. Whereas a student from India, he's got his maths log tables, and he will be able to, or she will be able to do it. Pop, 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 like that. And I could do something like this. These days I have slowed down because I'm also lazy now using calculator, but I could do it. So let's go over the theory of what this log is all about. To understand this, we need to look at the graph of a power x. Suppose you have a curve y equal to a power x. Do you realize when x is 0, x belongs to R? And a is a positive rational number. I don't want to go to irrational numbers at the moment. So, or just a positive number. Then, when x is 0, 1, what happens when x increases? It keeps on going up and up and up and up. A is actually greater than 1. If a is less than 1, it's going to be a problem. So, let's put a greater than 1. So, then, this graph goes like that. Right? This is the graph of y equal to a power x. So, if x was minus 2, it was a power minus 2, 1 over a squared. If x was minus 10, it was 1 over a power 10, 1 over a power 10. And if your a was 10, to divide is 0.10 zeros and 1, 0.100 zeros and 1, the numbers become unmanageable. So, what they did was, if y equals a power x, then they said x is equal to logarithm of y to base a. That is how it was defined. What was the use? So, I will show you how it becomes useful a bit later. So, in other words, you are now reversing the process of power. In fact, logarithms, actually, remember in functions, we talked about it finding an inverse. Logarithm of y, or the function y equal to logarithm of x to base a. Remember when we did functions, how to find an inverse? Start with the original function, y equal to f of x, and make x the subject. In the final answer, you write f inverse x in terms of x. So, I made x the subject, so I'm writing it in terms of x. This graph would be a graph like this. Now you see, for large values of x, a power x is going to infinity. Here for large values of x, log x is also going to infinity, but at a much slower rate. That means my numbers are more manageable by using this graph to solve than using that graph. And once I get an answer on this graph, I can always reflect and get the answer on the other graph. That was the concept behind logarithms. In other words, when you have unmanageable numbers, use the log graph, find the answer, and then you go back by reflection to find the original number. So that's the definition of logarithm. I'll just write it, and then we will go over. I'll write the rules, and I'll show some of the rules as well and see how to apply them to questions. right? So if y equals a power x, then x equal to logarithm of y to base a. Okay? Then the rules are very simple. Log 1 to base a is 0. Logarithm of 1 because look, the original graph of a power x was cutting at 0, 1. When you reflect it in y-axis, sorry, the line y equal to x, the inverse cuts at 1, 0. This is the graph of y equal to log x to base a. Remember, I didn't know what is a, but I know it will always cut the x-axis at 1. So therefore, log of 1 must be 0. Also, if a number is less than 1, log will be negative. If the number is more than 1, log will be positive. Remember that? And the second one was log of PQ to base A is log P to base A plus log Q to base A. I'll prove this result, some of them, to show you. Similarly, log of P over Q to base A is log P to base A minus log Q to base A. And log of log of A to base A is 1. And log of P power n to base A is n log P to base A. How life becomes easier, once I'll show you the proofs, and after the 1 or 2 proofs, and then I will show you how to apply them and how life becomes easier. Okay? Because you will be wondering, sir, but we have the calculator. Why do I have to do this? But please spare a thought to those children in India, those children in Africa, those children in China who are not allowed. Imagine suddenly your dad is a diplomat or a famous football player and he goes and joins a club in China. And you have to, comes to India to play for cricket maybe in the IPL league. Then you have to move to India. Then you're going to, the place where you're in, there's no British school, so you have to still go to school. So you're going to do the Indian A level. You don't have a calculator, my friend. You better know how to do this. Good. So let me prove, as I told you, you don't have to copy any of this. They will always be in the notes. Let me prove some of these results. And then I'll have to find questions or make up my own questions to make you understand. So prove, let's say, logarithm of AB to base x equal to log A to base x plus log B to base x. Remember the rule? If P power A equals P power x equal to y, then log y to base P equals x. The definition of logarithm. So what I'll do is, let log A to base x be equal to P. So can you say A equals P power x? Okay. Let log B to base x be Q. Then I can say Q equals P power, then I can say B equal to Q power x. So what is AB? AB equals P power x times Q power x. Yeah? No. What am I talking of? Log A to base x and log B to base x, okay? AB is P power x times Q power x. Very good. Now, how am I going to link this to that? I don't know. I don't know. This, can you see where I've gone wrong? Look at this. If p power x is y, log of y to base p is x. That means log of the number to the base is the power. So log of the number to the base is power. So this is x power p. This is x power q. You know, I took this intentionally because I have come across proofs like this in my test when I mark. Students then cook up somewhere. But some of them did this. They went back to the definition and realized. So therefore, this will be x power p. I wanted to show you, I mean, sometimes I do commit mistakes, but today I knew what I was talking of. I purposely did it to show you how, if you're not careful in applying the definition, you can go down a blind alley and you don't know where to go from there. So, what is x power p times x power q? So, can I say x power p plus q equals ab? Meaning, now, the number x raised to a power is the answer. So, remember, number p raised to power x is the answer y. So, logarithm of the answer y to the number p is equal to the power. So, logarithm of the number ab to the base x should be equal to p plus q. But what is p? So, logarithm of ab to base x is equal to p is log a to base x plus q is log b to base x. I have purposely not given one important rule in logs, which I will take up shortly. So you can try yourself proving the other rules, like, you know, log of a over b, log a minus log b, and then a log of a power n is n log a, and so on. But there's one important rule which I have, of logs, which I have not proved. I want to take it up and see what is log a to base b in terms of log a to base x and log b to base x. Sometimes you come across logarithm of 4 to base 2 or logarithm of 17 to base 5. How are you going to do that? So, I need to find a relation. So, let's call log a to base b as p, log a to base x as q, and then log b to base x as r. I'm indirectly doing the proof. So, a equals b power p, a equals x power q, and b equals x power r. So, I can say x power q is equal to x power r whole power p. So, I can say x power q equals x power pr. So, therefore, q equals pr. So, what is p equal to? Q over r. What is p? Log a to base b equals, what is q? Q is log a to base x over r is log b to base x. That is change of base. Log a to base b is log a to base x divided by log b to base x. That's a very important rule in logarithms. So, of course, a log without a base is meaningless, but in the exam, you will say log x. Sometimes you will say ln x, sometimes they will say log x to base e, sometimes they will say log x to base 10. Sometimes some books use lgx and ln x, depending upon the textbook. Remember, LG means log to base 10. If there is no base, you have mentioned LOG or LG. The base is always 10. If you written ln in the question or in the textbook, it's log to base e, or the Neperian, or a natural logarithm. So a log without a base doesn't make sense, but by convention, when you say log, it is to base 10. When you say ln, it is to base e. You should know both. Okay? So I want to stop at that stage. I've introduced you to the concept of logarithms and show you the rules. In the next lesson, I'm going to list all the values, the rules, and then take examples to show you where and how you can apply logarithms to solve questions. I think I might take 2 lessons because there are quite a number of applications on this. Okay? Thank you very much. Have a good day. Bye-bye. Hello. I want to take this opportunity to propose a vote of thanks. I would like to thank Vivid Innovations Private Limited and Commerce Forum for so generously giving up their studio and the facilities and the services of their technicians to record all these videos for free. I think that needs to be acknowledged and appreciated. Thank you very much. And my special thanks to Mr. Nitin Mahadevappa, Mr. Nishant Guruswamy, and Mr. Sadan Kumar DN for all their help and assistance in getting these videos ready, uploaded, and launched. Thank you very much.